So the answer to the question I'm sure you're all wondering is no, I'm not dead. I'm back today with Codeforces round 740. This is a Div 1 round by Tourist. Let's jump right into it. Solutions will be at the end to everything I know how to solve. A tennis match consists of game. In each game, one of the players is serving, one's receiving. Players serve in turn after a game where Alice serves, follows by a game where Bob serves. Vice versa, each game ends in a victory of one of the two players. It's won by the serving player, then they hold the serve. It's won by the receiving player, they break it. Alice won A games, Boris won B. It is unknown who served first and who won which games. Find all values of K, such that exactly K breaks can happen during the match between Alice and Bob in total. So for one break, you have to switch who wins. So this is the same as 0-1, right? So in this case, you can have 0 breaks. How do you have 0 breaks? Oh, Bob wins the last one. So it's Alice, Alice, Bob. Or you can do oh, it switches every time. Yeah, okay. Gotcha. So you can, yeah, let's get out some paper here. So this is like, you have a you, and then a him, and then a you, and then a him, and then a you, for 5 moves, I guess. So you need, let's say you need 3 pluses, so you can give each plus to you, and then you have 0. Once you do that, you can add 2 times like the number of empty things on his side. So that can happen a few times. Oh, and this is the min, the number of times you get is the min of empty on his side, and pluses on yours. Okay. Or you can serve second. Yeah. So we got this, I think. So here's the idea. Alright, so then, yeah. So if A wins, we also need int total games. So that's how many pluses there are on the left. Int plus right will be A wins minus plus left. Int empty right will be total games over 2 minus plus right. So int min score will be, and then int empty left will be total games plus 1 over 2 minus plus left. Okay, so int min score is empty left plus right. And then int max add will be max.min of empty right and plus left. So we can move one of the pluses over each time. Okay, so now we need to do this a second time. This will be B first. Okay, and then sys out and set size. So then, what do we need here? This is different. So plus left will be this. Plus right will be same thing. This will be total games plus 1 over 2. Empty left. Yeah, this just like switch all these basically. I think that's fine. Let's try samples. Come on. Okay, it looks good. Yeah, I guess we'll submit. Oh shoot, no print writer. Darn it. That's dumb. Silly mistake. Alright, how's our time? 1.1 out of 2, so we're fine. Okay. Just for sanity. For my own well-being here. Okay. Let's move on to problem B. So this is a 6-round div 1, so non-trivial. But we'll see. Okay. Unusually low memory limit. Okay. We have a vertical strip with n cells, numbered 1 to n, from top to bottom. We have a token initially on cell n. We move the token up until it arrives at cell 1. Let the token be at cell x greater than 1 at some moment. One can shift the token in either of the following ways. Subtraction. You can choose an integer y and move the token from x to x minus y. So you can move the token any number of cells up. Floor division. You can choose an integer z and move the cell up by floor division. Find the number of ways to move this token from cell n to cell 1 using one or more shifts. Print it modulo m. What? Is this not just trivial? Oh, do we not have enough memory? Wait, what? Can we not just like do a BFS? Oh, division. There are lots of things you can divide by. Yeah, so the division is the hard part. So the subtraction's easy, division's hard. Voice crack, division's hard. Can we do the square root shenanigans? Probably not. Bro, this is a tough set. Tourist is not joking around. So read C. We've got a permutation of some array of integers from 1 to n. The length of the permutation is odd. We need to sort the permutation in increasing order. In one step, you can choose any prefix of the permutation with odd length and reverse it. Okay. Find a way to sort A using this many reversals of the above kind, or determine that such a way doesn't exist. The number of reversals doesn't have to be minimized. So if the prefix of odd length is always, oh, n small. Okay, nice. The prefix of odd length is always, the prefix is always of odd length, I mean. That means the things in even positions stay in even positions. Right? Yeah, so, yeah. How many turns do we get? 5n over 2. I don't really know what that means. Some number of turns. Okay, so, okay, so a couple questions. Let's say it didn't have to be of odd length. Can we sort anything? So if we want to flip two elements, we can move them here. So now we have 4, 3, 2, 1. We can flip these two, 3, 4, 1, or 3, 4, 2, 1, and then flip them again, 1, 2, 4, 3. So we can do, oh man, that doesn't actually sort it though. That just proves it's sortable. Well, we can get, we can move any element to the last position, and then any other element to the last position, right? We can do each of these in 2 moves. Move to the end, yeah. So you can move anything to the beginning and then to the end in 2 moves. So that's going to be 2n, or in other words, 4n over 2. But we don't have to do that for every element, we only have to do that for odd elements. So this is like, it's like about 2n over 2, okay. So we can fix for all of the odd positions, we can handle them after the fact. Is it after the fact? Maybe. It's, okay, so we can handle the odd positions. Can we handle the even positions too? Well, yeah, because it's just a separate array, but with even ones now. Yeah, okay. So we're going to be doing some stuff to the odds and then also to the evens. Ideally, we'd like to not mess things up. N is always odd, that's nice. Okay. So can we handle the last 2 elements of the permutation initially? It's got to be at an even and an odd position. So we want this to be at position 0, and this one to be at position 1 is what we're going for. And we have, I think, 3 moves to do this. 3 moves to put them there, or well, 4 moves, right? So we have 4 moves. To get them in the right place, and then we put both of them where they belong. Yeah, this doesn't seem hard, unless I'm missing something. So we have 2 elements. We need to get this one to the right of this one. We need this one here, in 4 moves. Oh, it is hard though. So we can put the 0 here, and then the 1 here. Yeah, this is tough. So what if we move this one? Yeah, so we can move this one over instead. So we get the 1 here, and then the 0 next to it, but on the wrong side. Oh, so maybe we do this as 1 move, and then we have so we flip. Oh, that's even though. Ugh, it's so hard. Okay. Oh, but we can kind of do it. So we can get, then we can get 1 and then a 0. If we do these 3, so okay, so we do these 3, then we do these 3, and then we do these 3. And now we have 0 and 1. And then we flip them at the end. Okay, and then we put them where they belong. Yeah, okay, so then we put the 0 here, and then the 1 here. So we abused the fact that the 0 started out in front. Okay, so yeah, so this is only if the 0 starts in front. So okay, so if you have 0 dot 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 and then a 1, then you have 0 to beginning, 0 to front, and then 0 to before 1, and then you have 1 goes to position 1, 0 goes to position 2, and then you have 0 goes to position 0, 1 goes to position 1, and then you have 0 to the end, 1 to before it. So that's 5 moves to get 2 things. Okay. So the next thing is, what if we have a 1 and then a 0? I need a new sheet of paper for that. Okay, we're getting here. This is a fun problem. I'm enjoying this. Thank you, tourist. Oh man, okay. These got lots more solves, but that's fine. So we have a 1 and then a 0 with some other stuff. So we could flip them. Oh, you can flip them and move 0 to the beginning. Yeah, so then you have 0. Yes, you do this. So the first move is to get 0 to the beginning. After which we're set. Yeah, okay. I think, believe it or not, you can do this in n log n. Please don't make the time limit so ridiculous that you need to. This would actually be a really cool problem in n log n, I think, anyway. Yeah, this would be so cool in n log n. Can you imagine? Oh man, beautiful problem in n log n. Anyway, this is C. Because we aren't smart, we're just good at constructing things. Okay. They guarantee sum of n is small. Good. N equals this. Int array A, read array size n. Okay, so we have n in the array. So this is bigger. Val will be n. Is this a permutation? Yeah. Smaller equals, smaller val equals n minus 1. Bigger val is greater than 0. Bigger val minus equals 2. Smaller val minus equals 2. Okay. So then we have int bigger index. Okay, so we probably also want swap, static void swap. Int prefix size, static array list integer answers, array list. It can always be, it can't always be done. What? Why can it not always be done? Oh, if the sorting doesn't work. Okay, yeah. So if there is, yeah, so if a at I mod 2 equals I mod 2, and this out minus 1, continue utter. So we should be fine there, and then this is the other case. So otherwise it's possible. So in this case, sys out answers.size, die in answers, sys out I plus a space, and then a new line. Okay, now we just need to do this part. So swap for this prefix size, we also need a. Array new a equals a.clone. And I equals prefix, or I equals 0. I is less than or equal to prefix size, I plus plus. Prefix size is 1, we want to go less than it. So then a at I equals new A at I, or at prefix size -1 minus A. Minus I mean. Yeah, and then that's it. Okay, and then we need answer dot add prefix size, and then we need answers dot clear, and then we're good here. Okay, so then crash if we don't get it. Alright, so then we have this. Okay, so first we move, yeah, that's the problem with this, right? That is the problem with this, okay. So the first thing we need to do is move bigger to the front. Swap end of bigger val. Then move 0 to before 1. Swap index of smaller val A -1. Then we move these to 0 and 1, so swap end of smaller val A +1, swap 3, swap end of, oh, I guess, okay, so now go to position equals n-1. Swap go to position A. So 5 things takes 2. Looks like we're good. What is the problem here? Is this wrong? Was new A at prefix size -1 minus I. Next of bigger val, 0, 1, 2. Yeah, so let's make the swap be one bigger. Just 2. Three, 1, 3, 3, 3. Seems plausible. N times 5 over 2, so 7.5, we're good there. This is just 2n, so we're fine there. It seems plausible. Yeah, let's just submit. No, wait, good, that is C, okay. Good. Nice job, ladies and gentlemen. Bro, this is a scary set. Okay, so how do you do B? Good question. The idea is like, we could easily, so if we only had like one division choice, it would be easy. The problem is we have square root n division choices. Yeah, so it's just up to this. So we can write a brute forcer pretty easily. I don't know that that's exceedingly helpful. What else? We can there are several ways to go from one to another that's considered distinct. Yeah, so we have, so we want to do something like, at some position, update all of the things you can reach by 1. So you can go here, or by your current value. You can go here several times. How many times can you go to 2? So 8 divided by 3, or 7. 7 divided by 3 is 2. 7 divided by 2 is 3, so this is twice. How many times to 1? So 4, 5, 6, 7. So 4. So there's square root of n ways of going to this. So each element what if we try and go the other way? So something we try and hit, what things have this divisible by 2? So these ones. Oh, so it would be, yeah, so we have this is the multiple, then this is a multiple, this is a multiple. Oh wait, it's gotta be this exactly though. So what things, yeah, so it's like what things divided by 2 are equal to us. So x over something is equal to me. How big can this something be? You could have x over 1, you could have x over 2, x over 3. Probably not that many things. Most square root, right? You know the other thing is bigger than you, maybe? No, can be anything. So we have this thing. X over some number is equal to me. Say x over 7 is equal to me. For which x's? So this means me is greater than or equal to 7x, and me is less than or equal to 7x plus 6, right? Or sorry, x is equal to 7me. That's backwards. Okay, so x is less than or equal to 7me. If it were bigger than that, me. Yeah, it can't be, if x is smaller than 7 times me, then x divided by 7, yeah, so 7 times me, that's a lower bound. And then it's less than or equal to 7 times me plus 1. Strictly less than that. Times me to 7 times me plus 1. Log squared with a bit. No, we can do prefix sums from the back. Yeah, I think this is harmonic. make it faster in a bit. First we'll just do the naive. So we need to say int I equals n minus 1 greater than or equal to 0, I minus minus. So we'll fill each of these things in from back to front. Then we need to say where it can come from. So int ans equals 0, and then call this dp, I guess. So then we'll say dp at fill in equals ants, and then we'll say at the end, sys out dp at 0. Do we go to 0 or to 1? So 1. Yeah, so we're doing this, okay. So now we need to brute force what we can come from. Yeah, so int I equals fill in plus 1 less than or equal to n plus plus. This is a for loop. Then ants equals add ants and dp at I. So we can come from any of the things bigger than us in one way. We can also come from a bunch of other things. So for int multiplier equals 2, let's just say true, and then say multiplier plus plus. So int lower will be multiplier times fill in. Int higher will be multiplier times fill in plus multiplier minus 1. Okay, and then if lower is greater than n, then break. And then higher equals math.min of higher and n minus 1. And then we can say for int I equals fill in, I equals lower, I is less than or equal to higher, I plus plus, ants equals add, answer dp at I. Okay, so this should in theory be correct. No, why not? Why not? True flow is bigger than or equal to n. Theory correct, and then this should be 25. This thing looks good. That's gonna tell you. Okay, so then, yeah, so we've got this. Now we need to make it fast. So int array cs, new int array n plus 2. So then we'll say cs at fill in equals cs at fill in plus 1 minus dp at fill in. Okay, these are two range sums, so we can make this fast. So ants equals sub dp at fill in plus 1 minus dp at n. Or n plus 1, I guess. Yeah. And then this should be an add, so we don't overflow. Wait, this should be a plus. And this should be an add. Okay, and then we need to say, we're doing this part. We need to, what are we doing here? So this answer is range sum, yeah. So we say the bigger stuff is on the left in this case. So this minus the thing after what we're going towards looks fine. And then we need range sum here too. So ants equals add answer, and then also we need a range sum here. So this will be dp, or this is not dp, this is cumulative sum for both of these. This is cumulative sum at lower minus cumulative sum at higher plus 1. Zero. Shoot. We just break everything? We did. Okay. CS at n equals 1. Alright, how many integers? This is 1,000,000 integers. That should be fine. It should be fine. That was slow, dude. Why was that so slow? Why was that so slow? It's order n. Oh no, it's n like n. Yeah, okay. Also, good lord, 6 seconds. Whew. Anyway, all right. So that's not terrible. It's a decent start, right? 54th place. That could be worse. Could be worse. We don't have to worry about losing to Monogon in this round. Here we go. Okay. It's also a little bit daunting. If none of these are geometry, we are in trouble. Geometry, not geometry. It looks like a tree or a graph. Okay. And this looks insane. There's no way tourist misplaces the difficulty on these problems. All right. Consider the insertion sort algorithm used to sort an integer sequence of length n in increasing order. For each I in order from 2 to n, do the following. If we're bigger than the thing before us, do nothing and move to the next value of I. Alright. Otherwise, find the smallest integer j, such that this thing. Shift the elements from j to I minus 1 position to the right. Write down the initial value of AI to position j. In this case, we'll say we perform an insertion. It can be noticed that after inserting any index I, the prefix of the sequence is sorted. Okay. For example, consider this. So initially we have a 4 and 5. Okay. Then we put the 3 in, and then we put the 1 in. Yeah. We're given an integer n and a list m of integer pairs. We're interested in the sequences such that if you sort them using the above algorithm, exactly m insertions will be performed. Exactly m. Okay. So we're given the length and we want is n less than m. Yeah, okay. First from, okay, yes. How many sequences of length n, not necessarily distinct, of integers, so not necessarily permutations, will satisfy this condition? So we have an upper bound, so it's finite. I see. Definitely not trivial. Oh, scary, scary. That's an easy wrong answer. People getting tripped up on that? Couple, maybe. Or maybe it's just a hard problem, who knows? This is not the right, why am I reading F? I don't care about F. All I care about is D right now. At this moment, that's it. Maybe should we read E? Well, what's the problem? It's pretty huge. There's a pretty big jump here. Yeah, let's stick to the lakes and rivers we're used to. Alright, I'm gonna get a Cliff Bar. Hungry. So it's just like, the insertion part doesn't really matter. We can kind of ignore the insertion sort part. It's just like, how many arrays are there of values from 1 to n where the number of new maxes is equal to this? Yeah. Importantly, for all test cases, the number of new maxes is pretty close, pretty close to the size of the array. So most things are a new max. Yeah, so if we have like some increasing subsequence, then we can insert something else in lots of positions. So it's like, so it's the number of like non-maxes, so less than max to insert. So here we have, I don't know, who knows, we have some number in every position. Is there even an easy n squared for this? So we could say for each thing. Oh, are the things independent? No. Oh, that's obnoxious. They're not independent. Yeah. Because if you insert 2 2s like in a row. Yuck. Disgusting. Okay. That makes it so annoying. Is that really true? Yeah, so we have some increasing sequence, and then we have some like non-increasing things. Now these increasing things can be a bunch of stuff, and the non-increasing things can also be a bunch of stuff, but they can also be at a bunch of positions too. But we know their order. So it's like how many ways can we interweave them, but like wait, what? Oh, we're giving it pairs. Solving the wrong problem over here. Okay, try number 2. I'm like, why is there so much input? If input's just 2 numbers, this should be easy. Okay. Alright. Read the problem carefully. Let's try this again. So, we have this many insertions. We're given what the insertions are, even. Okay. So, what are these x? Entry pairs. Exactly m insertions will be performed. The first one, position this, gets moved to position this. Alright. Okay. So we have some things, we have these ones, and now we have some element here that gets moved to this. So what does that mean? That means, let's say this is like some question mark, these are all increasing and they're less than or equal to the question mark. Less than or equal to, where does this get moved to? So this is a 3 to position 1, okay, and then position 3, yeah. So these are all less than or equal to, and these ones are all greater than. Alright, so we have got these things. Like, if you remove the things we have, remove the question marks, right? What does that tell us? The question marks are just like some increasing sequence. If we have any other increasing sequence, we have a question mark here. The question mark is just a divider. Okay, then we have another divider somewhere else that's bigger. And then another divider somewhere else that's bigger. Yeah, so if we know the positions of the dividers, is it stars and bars? Oh, we need to count something multiple times if it can happen multiple times. So, yeah, what if we did a simpler version of like A, C, B? So now we have this divider. So the number of times we need to count some pair of AC is equal to the difference between them plus 1. Just the difference between them. Guess we can make it slightly more complicated by doing like 2 on one side, 1 on the other. So if we knew what this was, we know how to distribute these with n choose k. Yeah, if we can brute force this. Is there any way we could end up actually brute forcing the divider? Seems unlikely. Seems like an n choose KDP. Well, the divider is really just like another thing, isn't it? If we have like A, B, C, like, you just lose a number. So it's just like not that like, alright, move the stuff to where they end up. Does that lose any information? No. Yeah, because the stuff before you oh, you can have two things inserted into the same spot. Yeah. Okay, so handle that, but other than two things inserted into the same spot, if you have some element, anything before it can't be n, and anything after it can't be 0. So you can just ignore the fact that it's a special element, and then anything can be anything. You just have to increase. Yes. Yes. So in this case, this would just be, so it would be 3 thing, or it's, we choose the 2 bars. So there are 3 numbers, and then there are 5 positions. So 5 choose 2 ways of doing it. Yeah, I think it's just n choose k. No? Should be. Should just be n choose k. Maybe let's do some examples on paper here. 3, 0. What does that mean? N and M. So there are 3 things and no insertions. So there are 3, choose 3. There are 2 bars. Let's 5, choose 2. What? Not cool. 10, yeah, okay. So that's dumb. 3, 2. So let's try this. Okay, so we have 1, 2, 3. First index 2 gets put in index 1. Okay. Then index 3 gets put in index 1. So we have like a fixed, we have a fixed, and then we have a thing. So these can be 0. So this can't be 1, I guess. So yeah, so these don't have anything that are the same. So we can treat them as just XO. And then it's part of the prefix. It gets moved to the first position, right? So is the answer? The answer is 1. Why is the answer 1? Find the smallest index j such that ai is less than j. Oh, we shift it to the end? We shift it to the end. Okay. So, what are we guaranteed? So this comes before, which means there's a jump here. There might not be a jump here. There might not be a jump here. So we just need to know how many mandatory jumps there are. Is that the case? Yes, I think that's the case. How many mandatory jumps are there? So there is... Yeah, what do we do here? So we have a number. This can be, in theory, anything. Then we move something before it. So that means there is a jump here. Okay. Then we move something before this, which means there is a jump here. So there are 2 jumps, 2 unreachable things, and then 1 thing left, so it's 1, choose 1. Okay. 5, 3. So we have 1, 2, and we have this goes to position 1. So there's definitely a jump here, okay. Then 4 goes to position 1. Goes to position 1. So there's a jump here as well. And 5 goes to position 3. 1, 2, 3, 4, 5 goes to position 3. There is not necessarily a jump here, right? Because it's right after an X, so we don't lose anything. Yeah. So we don't lose anything. These are connected. So we have 2 things to insert. There were initially 5 choices, but we lost 2 to jumps. So we have 3 choices. So that means there are 2 bars and 2 things. So the answer should be 4, choose 2. It's not 21. Why is that? fundamentally incorrect. Gotta love it. Why are we wrong though? It seems so, right? So yeah, let's do this one more time. So we have 1, who knows about that? We have 2, nobody knows. Then we have a 3, which gets put in position 1. Okay. Then we have a 4, which is even smaller, which also gets put in position 1. Okay. Then we have so 1 and 2, they cannot be either a 1 or a 2, which means they can be a 3, a 4, or a 5. Oh wait, there are 3 choices. Yeah, there are 3 choices. Why is it 21? Because we have multiple choices for the things we place. Crap. Yeah, okay. So that's the problem. Okay. So we have 5 things, really. So we have 5 things. We have how many choices? 3 choices? Because we have 2 bars, so 5 things, 3 choices. So this is, you have 3 bars, or so you have 2 bars, which means that 7 choose 5. Good. All right. So we're right. That's proof by AC. So now the question is, how do we do it fast so we can get this problem? This is easy mode. Yeah, we can get this. We can get this. Not bad. Wait a minute. Bro. I am in a good place this contest. This is right where I want to be. Because, like, if I get this, I look really good. If I don't get it, I mean, I'm still okay. And if I do get it, like, no one is beating me on problems. Like, a couple people, maybe. We only have an hour left. These problems have, like, other than this problem, there is 1 solve on the things I don't have. So I'm liking my outlook here. Do I have? I don't have CF predictor. Okay. Firefox. Going back. Started using Chrome because, regrettably, I kind of used it at work. So, it's easier to just have everything using one set of dev tools for personal projects. And do I not have CF predictor here? Look, give me my high rating. What is my rating here, please? Engine. Is this not rated for me? It is going on. Okay, so this is just a contest. Yeah, good. All right. Cool, let's do this. Problem D, please. So, when is there a forced jump? Anytime we move to something, move to position, that doesn't have an X right before us. Then we have a forced jump. So like if you have an X right before you, you might not have a forced jump, but you still might. But if you move to a position that doesn't have an X right before you, anything after you has to be bigger. It also isn't the end. Is it the end? and isn't the end, yeah. If you move to the end, well, you can't move to the end, so that's not gonna happen. So anytime you move to a position that doesn't have an X right before you, that means there are some things that maybe match you, and then everything after you doesn't. Okay. Also, if you move between two X's. Okay, or if, in other words, if you have an X after you. So, yeah, okay, I see. So we need like some stuff here. We need like an array of sorted elements. So yeah, let's keep a array of sorted positions. We'll keep these in a bit, I think is the spoiler alert here. And then we need plus equals everything greater than or equal to us. We need, yeah, it's gonna be log squared. So should probably be fine. So plus equals everything bigger than us. Plus equals 1 always. Yeah. And then is X an array to see is there something bigger than us or smaller than us. And then append whatever. Yeah, okay. Oh man, this again. Two-factor authentication is just so annoying. You know, it's just like very, like, let's move on with our lives here, please. 8, 5, 6. Where's my bit? Well, we'll just do this manually. Okay. So, what do we need? Strip. Oh. Yeah. Okay, good. So static class insertion in from position into position. Are these sorted in? What am I looking at? Stop looking at problem B. Okay. Are these? The X's are sorted. X's are from. Okay. What do we need? We're gonna need nChoose k, right? Yeah. Static int mod equals this thing. Is our bit gonna need to be fast? No, bit can be slow. Or bit doesn't need mod. I mean, static long multiply. This will need to be longs. Static long fast pow. Long base. Long exponent. If e is equal to 0, return 1. Half will be fast pow of base to the exponent minus 0 over 2. If e mod 2 is equal to 0, then return multiply half by half. Otherwise, return multiply half by base. Yeah, okay, so then static long inverse of long x, return fast pow of x to the power minus 2. This is mod inverse, or mod minus 2, excuse me. And then what else do we need? We need n choose k, or we need precomp, static void precomp. Long array facts inverse. Facts at 0 equals facts of 1 or equals 1. That equals 1 less than facts less than max facts plus facts at I equals multiply facts minus 1 by I. So we have all our factorials. Let's make it static, and then we can just do this naively, I think, right? Because this should be fine. Yeah, so 4 and I equals 0 less than max fact plus facts inverse at I equals inverse of facts at I. Alright, static int n choose k, int n int k, return multiply facts at n by fact, or by multiply facts inverse at k by facts inverse at n minus k. So we have this. This is a long, and then we need to pre-comp here. What I just did here. That's slow. Okay. Yeah, I guess we'll just leave this how it is. Until we TLE. How much time do we have? 3 seconds. Should be fine. Okay. So, or we could just like do this the smart way, but that's fine for now. Okay. So we have this. So now we need to do the math. So what is this? We need to or not the math. We need to just calculate how many forced increases we have. So insertion array, insertions. There's new insertion array and insertions. Okay, this part does not really matter at all. Yeah, this doesn't matter. Or does it? It does. Does it? No, only the position we go to matters. Alright, I have to go to the bathroom. Be right back. This doesn't matter. This is all that matters. Okay, so we need a bit. Well, fine, we'll just read them in. So now, bit, so this is the array. That's not confusing at all. And insertions. Yeah, this makes total sense here. Okay, so now, for insertion, so we need a bit int n things in int value. So we need this. We need static boolean oh wait, we can get kth. Oh, that's cool. Cool. Yeah, that's cool. This is like the frequency. So we have like a frequency counter for this. Okay, and then we say well, it's not a frequency counter. Yeah, what are we doing? How do we do this? Okay. Man, this is not that hard. We have a list of sorted positions, right? So we have a list of numbers. We need to say, does this number exist? Does x exist? And then we need to say, insert or we need to say like add x, and then we need to say move all these things over by 1. So we can just like modify the query, right? Why is this so difficult? Does x exist? Add x, move suffix over by 1. I could just use a treep. Should I just use a treep? This is terrible. Why am I using a treep? This is such overkill. Does a thing exist? Add a thing, move everything over by 1. This should be easy. I mean, I guess I could just use a treep. And I need lazy propagation. Does my treep have lazy propagation? Oh boy. Oh boy, this is a mess. Okay. Treep. This is a mess. This is a disaster. Add. Yeah, so we have add. And then we have to prop. So I think we can just use this. This is a disaster. What am I doing with my life? Okay. Oh, this is terrible. So we have some stuff. Split, merge, recalc, prop, range add. So we need add. Yeah, so we're gonna want to add something. And then we need like range plus equals here. So we're going to want to split on value. Okay, so that's it. So we need treep. I guess it's just treep equals null. So we need to check if x exists. If exists ii dot to position, then treat. Then we still want to move everything over. Okay. So we have this insertion, so we want treat array parts equals split val, split the treat by ii dot to position. And then, yeah, so stuff less than and stuff bigger than or equal to. Alright, so we have these two parts. It exists, so we need int increases equals 0. So if this exists, increases plus plus, else if there isn't something smaller than us, so not exists, I dot to position minus 1 at parts 0. Increases plus plus, then treat equals merge of parts at 0, new treat, ii dot to position, and then parts at 1 dot to prop plus plus, treat equals merge treat, and then parts at 1. Okay, and now we have increases. Good. So now long ants equals n choose k. What is n? Well, we have all of the things, and then this is just n minus increases. Wait, what is this? This is not right. Okay, so this is n. So okay, so we choose the number of increases minus 1. That's how many blocks we have. This is n plus. Wait. Okay, so int actual things, or possible values, will be n minus increases, and bars will be possible values minus 1. So this is n plus bars, choose bars. 10, 1, not right. Okay, so then increases should not be 3. Considering 0, 0, 0. That's not 0, 0, 0. That's not right. Right? Shouldn't be. One, 3. Okay. So we have 1. And then we have 1, so this is an increase. And then we have 3 is not necessarily an increase. So this is what we're concerned with. So initially it's group 2. This thing doesn't exist, so we add it. So what is prop? Data is less than val. This is greater than or equal to. Yeah, okay. What the heck? What? Dude, what? I literally just passed this case. I just passed it. What? What the heck? So my treep's gotta be wrong then. It's the random. Alright. Why is this easy part of the problem causing me so many issues? Group 2. Okay, this one's saying it does exist. A 3 already exists. So how would a 3 exist? What? Oh, wait, I do. Oh, so it's saying it doesn't exist. So it's saying a 2 doesn't exist. Or it's saying it's saying a 2 doesn't exist. And less than and greater than, not my day today. Okay. So let's get this TLE and then optimize it. What do you say? We have print writer at least. No, okay, definitely TLE. Real TLE. Wrong answer 2. Darn, dude. Why is that? Okay. I think it's the treat part, or is it the other part? What is this problem actually asking? How many arrays are there where this is the case? Input is just 2 numbers, right? Oh, input is not just 2 numbers, it's a bunch of pairs. What if we have 3? We have 2 goes to 1, so 2 insertions, and then 3 goes to 1. So this should be 1. Alright, and then if instead this goes to 2, then we have x, and then an x, which might be the same. And then something bigger. So this can be 1, 2, 3. It can be 1, 1, 2. It can be 1, 1, 3. It can be 2, 2, 3. So there are 4 ways of doing it. We have exists, and then we have split val. We don't even need this, right? I guess we need merge. We have half an hour to get this a seed. Are the insertions always sorted? Yeah. Insertions are sorted. Okay. I don't know why I'd be wrong. We can't be the biggest. If there's something bigger than us, wait, what if there is something bigger than us? Oh, okay, so this logic might just be, logic might be wrong. Okay, so if we don't have an x right before us, we have no x right before us. That means we are an increase. Like this is an increase before and after. Okay, so, but if you have an x and then if you do have an x right before us, then you're fine. Don't have an x before us, or if we So this logic is not right. What if we have an x before and after us? So if we're inserting before an x, that means we should add 1. If we're inserting right after an x, what does that mean? We can be the same as it? So you have one thing here, okay? And then you insert here. So this has to be lower. Because you inserted before an X. If you had a thing here though, that wouldn't be the case. Okay. Then you insert after an X. So if you ever insert right after an X, it's ignorable. Is that it? Is it just the number of times you're not right after an X? Is this just it? I think that would be the case. So this would have been 4 things, 3 insertions, 2 to position 1, 3 to position 1, 4 to position 2. Okay, so we have here to this, so this is 1, then 3 to position 1, so this is less, 4 to position 2 is the same. So we have 4 values, but really you have 3 used. Or we have 2 increases. So we have 2 choices. Four, yeah, so 5 choose 1. Why is this so difficult? Okay. So, man, this is, I'm running out of time too. This is the worst, this is the worst. Okay. Oh, we have this treep. Well, let's try this with our old submission. This prints 5 too. It shouldn't print 5. Prints 1. $16. Okay. So, do we want another break case, maybe? So we have a thing. Well, what if we have 2 things here, 1 thing here, and 2 things here? So 5 things, 1 choice, which is 5 moves to position 3. So now you have, everything has 4 choices. You have 5 things, and then you have 3 bars, so 8 choose 5. Is that true? What does the brute forcer for this look like? So we try all pairs, see where they get inserted to. Okay. Max and add into array A. If add equals, and then we also need array list of int array. This is arrays. Okay, so what do we do in this case? This ours dot add A. That clone, and then return for into place equals 0, less than max, place plus plus, A at equals to place, and then get arrays at max at +1 A in ours. Get R's, arrays, the max is n, start at 0, new int array size n, and pass in R's. We need insertion. Then for int array I and R's. Static boolean works, int array A, and then insertion array inserts. Okay, so otherwise, if inserts at insert end is not equal to dot what is this? From position is not equal to I, then return false. If insert in is greater than or equal to inserts.length, or this, return false. Int 2 equals 0, while insert int, or while a at 2 is less than a at I, 2 plus. If inserts at insert end, that 2 position is not equal to 2, return false. So now a at 2 equals a at I equals 2 plus 1, less than or equal to I plus plus. A at I equals old a at I minus 1. This J. If works a insertions, then count plus. What the heck? Oh, insertion index plus plus. Trying this. Okay, so where are you going? man, I can get this problem. What am I doing here? I can get it. Oh. Okay. Man, what the heck? Okay, so position B. Oh, this isn't right. Okay, A at 2 equals A at I. Oh. Oh. don't have enough time here. Why is this wrong? If before, so this is a clone of the array. Array at 2 equals a at I. Go from 2 plus 1 up to j. Oh, j. Yeah, it's kind of annoying. Man, I don't know. This is my pre-comp. Am I missing mods somewhere? Seems fine. Could the bit be wrong? I'm not even using the bit. I'm only using the treat. I don't know why it would be wrong. I don't know. Darn, dude. Darn it. That's annoying. Okay, gotta change something real quick. Man, that's annoying. Alright, so yeah, let's take a look at the scoreboard here. What's going on? So do I just not have CF predictor? Codeforces predictor is just down for the day, I guess. Alright, anyway. So, I don't know what was up with this. I'm interested in what I got wrong. Can I see it now? No. Anyway, yeah, so I don't know about that. I guess let's look at the div2 problems, and then we'll talk about solutions real quick here. Oh, that's interesting. Okay. So, simply strange sort, so we have some permutation of distinct integers from 1 to n. Considering the following algorithm of the permutation increasing order. So a helper procedure of the algorithm f takes a single integer I and does the following. If a at I is greater, so if it's a decrease, then they're exchanged. Okay, so it swaps them if they need to. The algorithm consists of iterations numbered with consecutive integers 1 to n. So if it's odd, swap maybe the first two, then the next two, the next two, the next two, the next two. If it's even, swap these. It can be proven that after a finite number of iterations, the permutation will be sorted in increasing order. After how many iterations will this happen for the first time? So you can just do it, because it'll be n squared worst case. So yeah, you can just do the operations. Yeah. So if you just implement it, then that'll be the solution, I think. There might be a cleaner way of doing it, but that definitely works at least. So yeah, so you just simulate it, right? So just consider swapping the first two if you need to, then considering swapping the next two, and so on. Starting with these two, and then go back and then consider swapping the next two. You can prove that it'll finish sorting after, it's like bubble sort times 2, so it's at worst twice as slow as bubble sort. So it'll finish, and there you go. Awesome. So yeah, so that's the idea for A. Just simulate it and then check after each step. In problem B, you can also kind of simulate the thing. So the idea is, you know that for the first, well, let's, yeah, okay. I guess we'll try and explain this here. So maybe we can get out some paint, draw with a mouse here. So we have, yeah, so in tennis, the way the game works is you have some turns by the left player and then some turns by the right player, where the left player serves and then the right player serves. So let's try and minimize the number of breaks, and a break happens when the serving player is not equal to the player who wins. So what will happen is the first game will be by the left player, and then the next one will be by the right player, and so on. And then it's possible there are an odd number of games, in which case we have something like this. So maybe we have 4 games served by the right, 3 by the left. So ideally, we'll make all of these pluses, because if we want to minimize the number of breaks, we want the player on the right to win as many as possible. So we'll have some series of pluses on the left, and then we'll have some series of, I guess, non-pluses on the right. And it's possible that we'll overflow or we'll underflow. So in this case, we don't have enough pluses to fill all of the serves the left player wins. So we're going to have this one break here, but we might have too many as well. So in this case, maybe we have all of these cases. The first player wins all but one match, which means we're going to have at least these 2 breaks on the left. So let's look at this case. So now what will happen here is this is the fewest breaks we're able to get. We can always increase the number of breaks we have by 2 by having this win switch to this player. And that it'll create a break here. It'll also create one break here. So the left player will now lose a game, and the right player will now win a game where he didn't serve. So yeah, that's the idea. And that will give you all possibilities where the left player starts. Now it's also possible the right player starts. And in that case, you want to know how many games Alice wins. So if the right player starts, that means Alice is Bob, or Alice is so Alice is on the right. So that's possible as well. In that case, you just have to start distributing the extra games to the right player like this. So now, in this case, you could do something like this. So maybe it's possible Alice wins these 4, and then if you want, you can add 2 games to the right side. As long as 2 conditions are met, you need more empty spaces on this side, and you need more pluses on the left. So here you have, it's the minimum of 3 and 3, but if we had something like this, then it would be the minimum of 3 and 4. Or if we had 2 more games like this, maybe, then it would be the minimum of 3 and 2. So it would be up to 2 times 2 games. To implement this, I put all of it just in a hash set. So this was my code for it. So this is the number of pluses on the left, and this is the number of pluses on the right. You just math it out, assuming Alice goes first. And then you can store the number of empty squares on the right and empty squares on the left. Yeah, again, these are just mathed out. So this is the minimum possible score. And then repeatedly, you can take one of the games that the left server won and move it to the right. And then that will maintain the number of games each person wins, and then increase the number of breaks by 2. So I add all of these to a tree set. This will make sure I don't double count anything, and then it'll also sort them for me. And then I try it where Bob plays first instead of Alice. And this will get me all of the other possibilities. The only difference between the code here is that, like, anytime I was doing this is like a round up when you divide by 2, and this is a round down. So I would switch which of these I did. That's the only difference between these two blocks. Yeah, so that's the idea to problem A, or problem B in div 2. I guess let's read problem C real quick. So in a video game, a player controls a hero characterized by a single value power. The hero will have to beat monsters that are also considered by some value, characterized by a value of armor. On the current level, the hero is facing N caves. To pass the level, the hero must enter all caves in some order, each cave exactly once, and exit each cave in sound. Safe and sound? Oh, exit each cave, safe and sound, gotcha. When the hero enters cave I, he will have to fight K monsters in the first row. First a monster with armor this, then a monster with this, and so on. A hero can beat a monster if and only if the hero's power is strictly greater than the monster's armor. If the hero can't beat the monsters he's fighting, the game ends and the player loses. Every time a hero beats a monster, the hero's power increases by 1. Find the smallest possible power the hero must start the level with in order to be able to enter all caves and defeat in some order and beat all of the monsters. Okay, so here you need 43. Here you need 13, so 14, 15, 16, yeah, okay. So, yeah. So what you can do here is when you're fighting monsters in a certain order, I guess let's look at the second example here. So we have one cave that looks like this. So it's 10, 15, and then 8. And then this one is 12, 11. Alright, so what we can do here is we know whenever we're fighting the second element in some row, we'll already have beaten the first element. So we can effectively just subtract 1 from this total here. So instead of this being 15, we can make it 14. Instead of this being 8, we know we'll have beaten the first 2 if we ever get here. So this will really be 6. And then similarly, this can be 10. So now we have these updated things, and the important part here is that the minimum of some row, or sorry, the maximum of some row, is what your starting power needs to be bigger than for you to be able to beat the entire row. So in this case, to beat this row, your starting power needs to be at least 14. To beat this row, your starting power needs to be at least 10. Sorry, JK, it needs to be at least 12. Because the maximum in the first row is 14, the maximum in the second row is 12. Now, that's all well and good. And what that will tell you is, we know when we start this, because when you start a cave, you have to complete the entire cave before you can leave. So when you start this, this will tell us, okay, this starts as 12, so we are going to want to take on this cave before we take on this cave. And then we can just say, okay, well, when we take on this cave, let's say we start with 13 power, because we need more than 12, that's the smallest we could possibly be. After we finish it, we'll have 15 power. And then once we have 15 power, we'll consider taking on the next smallest cave. In this case, it's this one here. That's the 14, it's the only one left. And we have more than that, but if we didn't, we would have to increase our starting power by some amount. So if we had to increase our starting power by 2, for instance, then, well, our starting power would be 2 more, and then we would add 2 to our current power. So that's kind of the idea behind that. And you can just basically have each row, for each row, calculate what would your starting power need to be if you enter this row, and then sort the rows by that value, and then go through them and say, okay, can I beat this with the current amount of power I have? If not, how much more power would I need to start with? And then add that value to my current power, and then we can just print the answer at the end. So the runtime of that will be the sum of ki plus n log n. If you sort. You might be able to do better, but like you might be able to abuse the fact that the sum is small with some radix sort, but that's plenty fine. So n log n runtime basically for that problem. All right, so what is this? Oh, yeah, okay. So this is up the strip. Okay, so this is, yeah, cool. That's nice. That's a good problem, actually. So for up the strip, this was div 1c. It wasn't actually that bad. No, it was div 1b, JK. Wasn't that bad. But we didn't have the difference here. So for D1, they made n a little bit smaller, which let you use square root factor in it. So I'll talk about that general idea here for a minute. So the idea is you have a bunch of values. So you've got, use black here. You have 1, 2, 3, 4, 5, 6, 7. You start at value 7, and then on each turn you have two choices. So either you can subtract any number from 7. So maybe you choose to subtract, what is this, 3, and you go to 4. Or you can subtract 2. Alternatively, you can divide any number from 7. So maybe you divide 7 by 3, and that's 7 divided by 3 is like 2 with some remainder. So you drop the remainder, and 7 divided by 3 is, we just call it 2. So you can divide by any number from 2 to 7, or you can subtract any number from 1 to 7, or from, I guess, from 1 to 6, because you can't get to 0. So the question is, how many ways are there to get to 1? So one way might be you subtract 3, and then you divide by 2, and then you subtract 1. So this is a minus 3, this is a divide by 2, and this is a minus 1. Alternatively, what you can do is you could take the same path, but you could subtract 3, you could subtract 2, and then you could divide by 2. And these both count as two different ways. Even though the jumps you take are the same, this is two different ways. So we can do this if we're gonna do a naive DP, we can do an n squared pretty easily. What we'll say is, like, for each position, we'll start at this position, and then we'll say how many ways are there to get to each smaller position. So we're gonna process the positions from right to left. So we'll start with the 7, and then we'll say, okay, let's say we have one way of getting to the 7. So then we'll mark how many ways are there of getting to everything from the 7. So we have one way from the 6, one way from the 5, one way to the 4, one way to the 3, and then we'll do all of those for subtraction. Then we also have to add them for addition as well. So then we'll say, okay, you can, or for division as well. So we'll go to 3. We have one way of doing that, because 7 divided by 2 goes to 3. Then we'll try 7 divided by 3, 7 divided by 4, 7 divided by 5, etc. And that'll be n squared. That'll be a nice, pretty easy solution. The problem is that's not going to pass. So how do we speed it up? Well, the key observation here for the easier version of this problem is that there are only square root n things that if we have 7 divided by x, that this can hit. It'll hit everything smaller than the square root. So, like, let's say x is a big number. If x is a big number, right, if x is bigger than the square root of 7, then this value is going to be less than the square root of 7. If x is big. If x is small, then it might be bigger than the square root, but there aren't that many versions of them. Right? If x is a small number, there are only square root n things smaller than the square root. So in total, we have like less than or equal to 2 times the square root of n things that n can reach. And we can calculate for each one of those, like we know what all of those things are, we can calculate for each one of those, how many times does it hit n? And then we can update each of them individually. So that'll run in n root n time, but we can speed it up. So that'll pass for D1. It won't pass for D2 though. For D2 we need another slight optimization here. And that optimization is we can look at things in a slightly different way. So previously what we were looking at is we wanted to say for some value we want to update all of the things it reaches. Instead, we can say for some value, maybe 3, what things can reach 3. Actually, let's look at 2. It's a bit more interesting. Let's see what things can reach 2. So any of these things in this array all of these will have an edge to 2 because they can all subtract. So we can find a range sum on an array here. Now we want to look at, like, okay, we have some number, x, divided by something, and this is equal to 2. What we can do here is we can brute force what this thing here is. So let's say x divided by y is equal to 2, maybe. We want to find the sum of the dp values for all these different x's. So in this case, 4 divided by 2 goes to 2, 5 divided by 2 also goes to 2, 6 divided by 3 goes to 2. So we're going to brute force what this y is, and it turns out there are like not that many choices for the y. Once x starts to get big, there are only a couple choices for the y. So when x is n over 2, you only have at most 2 choices for the y, right? And when x is n over 3, you only have 3 choices for the y. So if we brute force y, our total runtime is going to be harmonic. It's going to be like n over 1 plus n over 2 plus n over 3. And this is at most, this turns out into be n log n. So our runtime is going to be harmonic, which is going to be fast enough for this case. So we're going to brute force the y. We need to know which x's, if you divide them by y and floor the division, reach 2. So it turns out that those are the x's which are bigger than or equal to y times 2. And then they're less than y plus 1 times 2. Hopefully you can read my kind of gross handwriting here. So yeah, so this is the range of dp values we want to add to. So in this case, this would be this range here. So all of the values that are JK. What am I doing here? So it's this range here. So the things between 2 times 2 is 4, and then the things that are between 4 and less than 6. We add these for this case, and then for this case we'll add this range here when y equals 3. Yeah, so that's the general idea. What does the code look like? So here's the slow code, but you can speed this up just by using cumulative sums, and it looks like this. We'll have this dp. Initially there's one way to get to n, and then we brute force which thing we're going to fill in, and then we look at all of the possible multiple values that it could have, which are all of these y's in this situation. And then we calculate these two things, and then do a range sum, and add that to our possible answer, and then fill in the dp at the end. So yeah, that's the solution to problem B. I'll also talk about C real quick here. So this was problem E in the div 2. But you've got this permutation, and you're doing some stuff with it. Basically, the operation you can do is you can pick some odd length prefix and reverse it, and then you want to sort the array. So a couple observations here. The first one should be somewhat clear, but let's look at what we're doing for a moment here. So if you have some things, we'll make 7 of them because that's a good number, and you pick some odd prefix and reverse it. What happens is all of the odd positions stay at odd positions, and all of the even positions stay at even positions. That's an invariant which doesn't change, which means any number that starts at an odd position can only move to other odd positions, and vice versa. So that tells you right away that if any odd position element needs to move to an even position element, it's impossible. You can prove that it's always possible to sort other than that case. So if you ignore that case, it's always possible to sort the things, but it's not possible if that condition doesn't hold, right? If something changes the parity of its position in order to become sorted, then it's impossible. So we can really easily eliminate all of the cases where it's impossible. What we're left with is we need to now construct some way of doing it. And here's the idea. We're going to step by step place the last 2 elements in the array. So we're going to come up with some algorithm that does that. I'm going to call this position A and this position B. So we want to find, okay, where is A in the array? Maybe A starts here, and then where is B in the array? B will start here. Importantly, A will be on an odd position and B will be on an even position. So let's say B is here actually. Maybe that makes it a bit easier. So the first thing we're going to do this in 5 steps. We're going to take 5 steps and we're going to put the last 2 things at the end. The first thing we're going to do is we're going to move A to the beginning. So we'll do that like this. So after that, we'll have we'll have A here, we'll have B here, and then we have some other circles around here. So this is step 1. And in step 2, we'll move A right next to B. So this is step 1. Step 2, we'll swap the first 3 things. So now we'll have something that looks like this. We'll have an A here. Oops. And then a B here. And then things like this. Okay. And now in step 3, we will move B to position 2. And then A to position 3. And we can do that by reversing this subarray right here. So then we would reverse this one here. Okay. Now step 4 is we'll put A in the beginning and then B in position 2. So we can do these 2, and then we'll have A in the beginning, and then B in position 2. And then we have our empty spaces here. And then we can very easily move A and B to the end right here. So now A goes to the last position where it belongs, and then B goes to the last position here. This is always possible, and the reason that it's always possible is because after this first move, when we move A to the beginning, B will be after it, right? And then the only things that's required to do these 5 steps is B has to be at like an odd index, and A has to be at an even index, or vice versa. Like, depends how you order them. But yeah, that's the idea. So since we can do n squared, this is actually a really easy problem to implement. It just looks like this. So if we have a swap method and an index of method, we can just do this. So we just do this for loop and then print the answers at the end. So it's really quite easy. Yeah, and that's the solution to it. So yeah, hopefully that helps. I also think I have a solution to this problem. Yeah, I think I have a solution to F, but apparently, I don't know, apparently it's not right. So I guess I'll leave it at that. Just solutions to the first 3. Hopefully that was helpful. I'm gonna try and figure out what on earth was wrong with my F sometime later today when I get a chance. But yeah, hopefully that was helpful, and hopefully you did well in the contest. Yeah, nice job to Rainboy. Did pretty well. You got F. Well done, sir. Well done. And yeah, I guess that's all for me. Have a great day. See you later.